This program is brought to you by Stanford University. Please visit us at stanford.edu.
All right, we want to move on to a slippery and somewhat abstract and, frankly, a little bit difficult subject. The notion, well, first of all, the subject is tensor calculus. We've done about everything that you can do with tensor algebra and tensor arithmetic, adding, subtracting. We haven't talked about adding and subtracting tensors, but you can add and subtract tensors. Just make sure the things that you're adding have matching indices. Don't try to add something like Vn to a W sub m. That will not be a good operation. If you want to add V and W, add contravariant components or covariant components. Don't try to add a tensor with 2 indices to a tensor with 3 indices. That won't make sense. What we have at the end, a scramble of garbage. But as long as you're adding things which are compatible, that they have their indices in the same place, same type of indices, then tensors add. That simply means that the sums and differences of tensors are again tensors, meaning to say that they transform the same way as the originals. Now, why do we introduce, first of all, why do we introduce tensors? Let's go back a step and talk about why they're important. We want to discuss the properties of geometries of various kinds. Geometry could be a sphere, it could be a torus, it could be just and it doesn't have to be 2-dimensional either, but for 2-dimensional, it could be a plane, it could be a hilly surface, which is highly irregular. And of course, we don't really need to draw coordinates on it. There are no coordinates really drawn on the Earth. Of course, we can talk about properties of the Earth without actually introducing coordinates. Most likely, we could express all of physics without coordinates, without introducing coordinates, but it would be difficult. When we actually come to compute things, it's very convenient to be able to discuss the components of vectors, tensors, and so forth. After all, I mean, computation is about numbers, not abstract symbols, and when you come to actually compute, to throw it onto a computer or something, you want to put in numerical values for things, and the components of vectors and tensors and so forth are the way that you describe them in practice. Now, tensors have the very important property, oh, well, all right, let's start. The relationships that we're actually interested in are relationships which, in a sense, are independent of the coordinates, which don't depend on your choice of coordinates. The fact that the Earth is a sphere doesn't depend on what coordinates you use. The fact that its curvature is everywhere the same, well, of course, it's not quite true. So let's say what is true. The fact that the Earth is almost a sphere, which is slightly flattened, you don't need coordinates to express that. The fact that Mount Everest is a lump on the surface of the Earth, again, you don't need coordinates to describe that. Those things are things which are coordinate independent. But what we want to do is express those same kinds of facts, geometric facts, in terms of coordinates. That means we want to write equations which perhaps the numerical left side and the numerical right side do depend on the coordinates, but the fact that the left side equals the right side should not depend on coordinates. So it's important to isolate quantities that have the following property, that if their components are equal, if there's a rule or if there's a fact that the components of one tensor, for example, or one object, and this object happens to have indices, may or may not be a tensor, may or may not transform the right way. It has some indices. In other words, there are whatever number of such objects there are, you lay them out in a matrix if you like. if we know that in one coordinate system, let's say the x coordinate system, if we know that two matrices, or two tensors are equal in the x coordinate system, then it must follow, or we're looking for definitions so that the equality in one coordinate system will imply the equality in all other coordinate systems. In that sense, if we can write our equations and our laws of physics in terms of objects which, if they are equal in one coordinate system, then they are necessarily equal in all coordinate systems, then effectively we've expressed the laws in a way which don't depend on the coordinates. They don't depend on the coordinates. Maybe perhaps the numerical value of the left-hand side and the right-hand side depend on the coordinates, but the fact that they're equal doesn't. All right, we can write that another way. We can always take any such equation, subtract this, and write that it's equal to 0. It's an interesting fact. The equality sign is completely unnecessary in mathematics. You could make it a rule, put everything over on one side, and whenever you see an expression, assume that it's 0, and then you never need the 0 sign. You never need the equality. This is 0, because that's our definition, but we don't do that. We allow ourselves to use equals and 0. And so the same statement that I just made, is that we would like to express our equations of physics in a form, something is equal to 0, and if that something is equal to 0 in one coordinate system, then it's 0 in every coordinate system. We would like to find objects which have that property. Those objects are tensors. How do I know that? Well, let's just remind ourselves how tensors transform. A tensor, for example, a vector, let's just take the simplest case, a vector, Vn of y, in other words, the components of a vector in the y coordinate system are equal to the components of v, the same vector in the x coordinate system. We can put an r here, and then there is a, let's see, which way does it go? N is downstairs, so there's a dy n dx r. Whoops, put the n r. All right, so now it's quite easy. If all of the components, not just one of the components, but if all of the components of Vx are equal to 0, then all of the components of Vy are equal to 0, obviously, just from this equation here. If all of the components of V are equal to 0, in other words, if V is a vector which is equal to 0, then its components are 0 either in the y coordinates or the x coordinates. So with transformation properties like this, or more complicated ones involving several indices, for example, if we have some tensor, let's put one index upstairs, another index downstairs. In the y coordinates, that would be equal to dym by dxr, dx s by dyn times t rs. All right, again, if all of the, in the x coordinates, if all of the components of t are 0 in the x coordinates, then all of them are 0 in the y coordinates. That's the importance of tensors. That if you have an equation which is true in one set of coordinates, and you know that the objects are tensors, you don't have to check them in other coordinate systems. Now we're going to discover that not everything is a tensor. In particular, ordinary derivatives of tensors are not tensors. Not everything that you can write down is a tensor. But still, we want to define some sort of notion of the way a tensor varies from place to place. It's going to be important to have an idea of how things vary from place to place, so we have to have some concept of the notion of a derivative of a tensor. Let's go through why it's problematic. Okay. Let's start with scalars. Incidentally, the transformation property of a scalar is trivial if the scalar is phi, we call it this typical scalar phi. If its value at a certain point in space is phi in the x coordinates, then it's also phi in the y coordinates. If the points x and y correspond to the same actual material point here on the blackboard, just different coordinate representations of the same point. So phi transforms in a trivial way, doesn't transform at all. Obviously, if you know that phi is equal to 0 in one reference frame, you know that it's 0 in all reference frames, simply because it's the same in all reference frames. Now let's come to the derivative of phi with respect to x. The derivative of phi with respect to xm, let's say. All right? That is, in fact, a vector. It's a vector with a covariant index here. But let's just see, why is it true that if mathematically it's straightforward, the fact that if d phi by dx is equal to 0, then d phi by dy is equal to 0. Mathematically, it's just that d phi by dy, let's call it yn, is equal to dx m by dy in times phi times the derivative of phi with respect to xm. So if phi is constant and has no derivatives with respect to x, clearly its derivatives with respect to y are also 0. But let's just think about it from an intuitive point of view. To say that phi has no derivatives, in particular, let's imagine it has no derivatives anywheres. What does it mean? That means it's constant and it doesn't vary from place to place. It's a scalar. You could go and measure it in every point in space, and it's constant, like the temperature being the same everywhere in the room here. If a thing is constant, it's going to be constant no matter what the coordinates are. I don't care whether I use polar coordinates, I use elliptical, hyperbolic, Shmulevitz coordinates, doesn't matter. Whatever coordinates I use, if the temperature is constant in this room, it's going to be constant in every set of coordinates. So it stands to reason that if the derivative of phi is equal to 0 everywhere in space, with respect to x, then it's also going to be 0 with respect to y. So a perfectly good description of the air in this room in thermal equilibrium is that the temperature with respect, the derivative of the temperature with respect to the x coordinates is equal to 0, and you don't have to ask, will it also be 0 in the y coordinates, for the reasons I've just explained. Now let's come to vectors. And we're going to see that the problem is more complicated. Let's begin with a vector which is constant on the blackboard in space. Flat space, good old Cartesian coordinates. Let's not get fancy with curved space or anything, just ordinary flat space. Could be two-dimensional, could be three-dimensional, but let's take the blackboard, which is two-dimensional. Let's put some Cartesian coordinates, and let's also imagine a vector field which is constant in space. Now what that means is it points in the same direction everywheres, and it has the same length everywheres. Just the obvious meaning of saying a vector is constant. So every place in space, that vector is exactly the same. Now, what can you say about the components of this vector as you move from point to point? In the same coordinates, x1 and x2. For example, let's take the covariant components. Covariant components being the projections onto the axes. It's pretty obvious that the components are also constant. So to say that a vector is constant, it looks like what it says is that the components of the vector, what did I say, a covariant vector or a contra, let's say covariant components. Take any component and vary it in any direction. If the vector is constant, it looks like it says that the components are constant. But now, let's come and introduce some curved coordinates into space. Same physical fact, the vector points in the same direction everywhere, but now let me redraw it. I think I'll redraw it with some curvy linear coordinates, exactly the same situation. So the situation now is we have some curvy linear coordinates. And we have a constant vector. It means physically the vector points in the same direction everywhere. What about the covariant components of the vector as I move from place to place? You think they're constant? Remember what the covariant components are. They're the projection onto the axes, but the axes are bending and moving around on you. In one place, the axes might look like that. Someplace else, they might look like this. The same vector will have, this might be your x1 component, this might be your x2 component. Now this might be your x1 component, and this might be your x2 component, pointing in entirely different directions. The same vector, exactly the same vector pointing in exactly the same direction. I don't think I made that look the same direction, did I? The components will be different. The lesson is that just because a vector is physically constant from point to point in space, it does not mean that its components are constant in space. Why not? The components of a vector depend on two things. They depend on the direction and magnitude of the vector, and also the orientation of the axes. Even if the vector doesn't change when you move from place to place, the axes do. So, yeah.
To say the vector is pointing in the same direction and has the same magnitude implies a third coordinate system that is transposable. It applies to both of them, right?
I don't know what that means. Two coordinate systems. In this particular case, one of them is good old Cartesian coordinates on the blackboard. And we imagine, they're just good old intuitive Cartesian coordinates. And the vector is constant, which means in Cartesian coordinates, it means the components are constant. The same situation when we lay some curvy linear coordinates on the blackboard. Oh, incidentally, we could change from one Cartesian coordinate system to another. We could rotate or translate the Cartesian components. As long as the coordinates are Cartesian, then the components of the vector will be the same everywhere. But now we lay on top of it a curved coordinate system where the direction and spacing, for example, between the coordinates varies from place to place, and now the components will not be constant. As I said, it's because the components depend both on the vector and the orientation of the coordinates. If the coordinates are flopping around as you move around, the components will also be. So, dv by dx equals 0 does not imply that dv in the x-coordinate system, the components in the x-coordinate system relative to the x-axes, them being constant, which is the same as saying the derivatives are 0, does not say that dv m in the y-coordinates. This means the components, not only are they functions of y, but they're the components in the along the y-axes. It does not say that these are 0. No such implication. What does that tell us? That tells us that the derivatives of v with respect to x or with respect to y don't transform as a tensor. If they did, then if they were 0 in one frame, it would imply they were 0 in the other frame. Frame means a set of coordinates here. So derivatives of tensors, derivatives of scalars are perfectly good vectors. But derivatives of vectors, meaning to say the derivative of the components, they don't transform as the components of tensors. That's a general rule, and you have to do something. You have to do something a little trickier and a little more complicated to define derivatives of tensors to make them tensors. The process is called covariant differentiation. Now, the covariant is not because it has to do with a lower index here. It's another completely different use of the term covariant. What it means, what it implies, is it's a form of differentiation which you can apply to tensors, which gives you back tensors. In particular, you can apply it to vectors and get back vectors. So let's see if we can figure out what kind of thing the covariant derivative might be. Let's start with a thing which is not actually a tensor, but let's check whether it's a tensor or not. In other words, let's sort of assume it's a tensor and then prove that it's not. All right, exactly this object. Let's write Tmn. In fact, I'll tell you what. This is intended to be a tensor, but this is intended to be a tensor in the x-coordinate frame. Supposing there exists some tensor whose x components in the x-coordinates, and x-coordinates I now mean, again, rectangular Cartesian coordinates. Let's suppose that there is some tensor, Tmn, of x, which is equal to the derivative of some vector with respect to x in the x-coordinate system. Then the question is, what must it be in the y-coordinate system? And in particular, when you transform it as a tensor, does it or does it not become the derivative, this is in the x-coordinate, does it or does it not become the, let's call it, well, derivative of v of y with respect to yn? Question. And the answer, as you might guess, is the answer is no. If I try to transform this object, pretending it was a tensor, I will not get the set of components which look like that. So let's go through it. It's worth our while to do it. I could just tell you what the answer is, but let's not do it. Let's do it with some care. Okay. We have an object which I tell you is a tensor, and it happens that in the x-coordinate system, its components are the derivative of x, of v, with respect to xn. It happens. Let's ask, what must its components be in the y-coordinate system? Well, if it really is a tensor, then its components must be dxr by dym. This is under the assumption that it really does transform as a tensor. In the y-coordinates, it must be That's the assumption that Tmn is a tensor. And if you know it in the x-coordinates, then you can write it down immediately in the y-coordinates. But now we can substitute what it is in the x-coordinates here, and that would just give us the derivative of xr with respect to ym, derivative of xs with respect to yn, and now I'm just going to plug in the assumed value of Tmn of x, and that's Vm dVm of x with respect to, oh, I want TRS, excuse me, I want TRS, so that's dV r by dxs. And my question is this or is this not equal to, question mark, is this or is this not equal to the derivative of Vm, I think, let's see, Vm of y with respect to yn. The symbol equals with a question mark doesn't mean it's equals. It means, is it equal? Not it is equal, but is it equal? Right? Is this true? This is how we might have thought, just like derivatives of scalars transform as vectors, we might have thought the derivatives of components of vectors transform as tensors. So we're checking out, is this object over here equal to this? Okay, so let's see if we can work it out. It's not terribly hard. Okay, let's see. What can we do with this? dVr of x by dxs times dxs by dyn. Does that ring a bell? Let's focus on this piece right over here. That's chain rule. Yeah, that's the chain rule. So what's in the red box there, let's put what's in the red box over here. It's first of all, well, not just what's in the red box, but the whole thing. It's dxr by d, what is it, ym. And now if I use a chain rule, I simplify this, and I just find it's the derivative of Vr of x, but not with respect to x, but with respect to y, with respect to yn. And we're asking, is this the same as this? No, 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 no. Is that what I'm asking? Yeah, I guess that's what I'm asking. dVm by dyn, yes, okay. Ah, yes. Now notice on the right side, we're checking, is this equal to this? Over here, I have something involving y, Vy. Over here, I have something involving Vx. So let's change everything on the right-hand side so that it's related to components with respect to x. That's easy to do. We just write that Vm of y, this is derivative with respect to yn. And now, how do I write Vm of y in terms of x components? Well, I just write that Vmy is the derivative of xr with respect to ym of Vr of x. All I've done here was use the transformation from y components to x components to rewrite what's over here. Just pure substitution. So now we have the question, is this equal to or is it not? Let's write it out again. Derivative with respect to yn I realize that this is a bit tedious and a nuisance, but I wanted to do it, the whole thing. What is it? dxr by what? Can somebody read it to me? dy sub m, and then vm of x, right? vr of x, vr of x. Okay, well, let's look at it. We have here the derivative of a product. The derivative of a product is the sum of two terms. Just the usual rule for the derivative of a product. Derivative of a times b is a times the derivative of b plus b times the derivative of a. And so first of all, this derivative can hit v. That will give me a term which looks exactly like this. It'll give me the term dxr by dym times dvr of x with respect to yn. That's exactly what I have here. Looks good. But it's not good because it's only one of the terms when I take the derivative here. There's another term.
You're saying the derivative of something equals itself there?
What's that?
You've written that the derivative of a quantity equals itself.
I did? I did? No, I didn't. Where? The derivative of this is equal to this.
What's in the parenthesis is on the right-hand side of the equation.
Sorry, what did I do? No, these are not the same. Here. Here the derivative is outside the product. Here the derivative only acts on the v. Look at the difference. Here we have derivative with respect to y of a product. Here we have a product of two derivatives. Not the same thing. Okay. Who asked the question?
I did.
Yeah, are you happy?
Yes.
Okay, good. All right, so now we work this out. The first term is gotten by allowing the derivative with respect to y to hit v. That does look exactly like this. So far, so good. But there's something else in there. And let's see what that other thing is. It's derivative with respect to yn of the derivative of xr with respect to ym. That's a thing, times vr. So the answer is it is not equal to the right-hand side. Let's just call it the right-hand side. In other words, this thing which I called a tensor has not transformed as a tensor. If I insist that this is the x components of the tensor, then it is not true that the y components of the tensor are just derivatives of v with respect to y. It's not true. Okay? Let's see what we can say. Yeah.
At this point, can you give a physical example vector field? Trying to relate to
An electric field which varies from place to place, but not in Cartesian coordinates, in some other coordinates. And this is what happens. What happens is just because the components of a vector may be constant doesn't mean it's constant in all frames of reference. This extra term gets picked up here. This is the term that's due to the fact that the coordinates are varying from place to place. Okay? After all, or the directions of the coordinates are varying from place to place. If we had if the x coordinates were linear functions of the y coordinates, then these derivatives here would just be numbers, and derivatives of numbers are 0. It's because the coordinates are curved that this is not 0 in general. And it's, as I said, it has to do with the fact that the relationship between the coordinates is varying from place to place. That's the way to think about it. The xr by dym, that's the relationship between the x coordinates and the y coordinates. And now that if it varies from place to place, then there's an extra term, and the extra term is proportional to v with no derivative. All right, so yeah.
Sort of like that picture right above.
Yeah, exactly like the picture right above. Except the red vectors could also be varying from place to place, and we see that there's an extra contribution. Look at the form of this. Let me write this in some. Let's see. What was the left-hand side? That's, I guess, this over here. That's what you would get if t really did transform as a tensor. All right? So if t really does transform as a tensor, this has to be the right answer. It differs from this over here. It differs from what you might have expected, namely this over here, by this extra term. That suggests that we have to do something a little bit different to differentiate a tensor and to get another tensor. Okay, and the difference involves an extra term which has not got derivatives of the vectors in it, but has funny derivatives associated with the relation between coordinates. Let's see. The right-hand side is, by definition, Tmn of y. I just read it off here. Assuming this is Tmn of x, then this must be Tmn of y because it transforms in the right way. I forced it to transform in the right way. And what we see is that that it has this extra term over here. It's not just, where is it? It's not just what you might have thought it was. Okay, let's try to guess then what the right way to differentiate tensors is. The right way must have an extra term that'll cancel this out. Let's just write this in another form. Let me call this object over here, let me give it a name, capital gamma. How many indices does it have? It has an index n, m, and r. One index upstairs, two indices downstairs. And it multiplies Vr. Okay. That's what we'll call this. Here's more or less what we discovered, in another way of saying it, that if we want to differentiate a tensor, its components, we have to do, and get another tensor back, we have to do something a little bit trickier than just differentiate its components. Namely, what we have to do is take the derivative of v with respect to y, or x, doesn't matter, x, the, let's call it m, n, and then add something to it. And the thing we have to add to it is just this gamma n, let's see, m r Vr. What this represents, what this term over here represents, is the fact that when you differentiate a tensor, you have to take into account the fact that the coordinates are varying from point to point. And so the components have some variation that's just due to the fact that the coordinates themselves are flopping around, so to speak. There's something here that has to go there. I haven't told you yet, well, I've told you in this language over here what this gamma is, but let's suppose, now we're making a guess. We're making a guess that if we could find the right object gamma, we could construct a new kind of derivative of a vector which contains an extra term, not just a derivative, but an extra term, which will make this into a tensor, which will make it into a tensor which we can call TMN. This process of differentiating is called covariant derivative. It's usually written as an upside-down triangle with an n downstairs. That means covariant derivative with respect to xn of Vm. And it's by definition equal to this thing over here if we can figure out what gamma is. If we can figure out what gamma is. Another way to ask it is can we find a thing called gamma? And I'll tell you what gamma is going to depend on. It's going to depend on the metric tensor. It's going to depend not only on the metric tensor, but the derivatives of the metric tensor. If the metric tensor has derivatives, that means in some way the coordinates are flopping around. If the metric tensor is not constant, it means the coordinates are flopping around. We're going to discover that this thing depends on the derivatives of the metric. Is there an object which has the property that when we construct the covariant derivative, what occurs is actually a tensor, really is a tensor and transforms as a tensor? That'll be a brilliant achievement because then we'll be able to write equations such as the covariant derivative of a vector might be equal to some other tensor, maybe a completely different object. The left-hand side could be the derivative of some electric field. The right-hand side could be some other tensor of a particular physical character. And we might have a situation, an equation, which says that the covariant derivative of the electric field is equal to some tensor. Will it be true in all reference frames? Yes, if the left-hand side is a tensor and transforms as a tensor, and also the right-hand side. So the question is, can we find this gamma? And that, whose nature it is to make derivatives equal to tensors.
Well, you wrote a gamma there. Is it the same gamma?
Yeah, that's one gamma, but remember this was a special case where the x's were Cartesian coordinates. Now it can happen that we have a geometry that cannot be described in terms of Cartesian coordinates, but still we'll discover that we can find a gamma which has the right property. All right. So the main purpose of this was just to show you that derivatives of tensors are not themselves tensors. You have to do something else. I'll give you the general rule. I'll tell you what the general rule is, in particular for tensors with lower, well, I'll give you the general rule right now. For things with lower components. For things with lower components, because the coordinates vary from place to place, there are contributions of this type for each one of the components. And I'll show you how it works, and then we'll see if we can find out any piece of information about what this gamma is. At some point, I'm going to leave for you a bunch of algebra to work out. But I'll show you what the rules are, and then you can go home and check yourself that I have the right object. Okay, so here was the way you write a covariant derivative of a vector. What would happen if I wanted to make a covariant derivative of a tensor? Oh, incidentally, what's the covariant derivative of a scalar? That's easy. It's just the ordinary derivative. Ordinary derivative is a tensor. Okay? But for a tensor, we have to do a more complicated operation. Let's take some tensor, not necessarily this tensor over here, any tensor, with two indices, for example, Tmn, and supposing we want to find its covariant derivative, again, with respect to y. Covariant derivative, I'll tell you what, I want to change notation here a little bit. I want to call this P. If I call that P, I have to call this P. So let's see, I have Tmn, and I want to take its covariant derivative with respect to p, with respect to yp. What does it have in it? Again, it starts out with the ordinary derivative, derivative of tmn with respect to yp. It starts out with just the ordinary derivative. That's all that would be there in Cartesian coordinates. But now, because the coordinates may be varying from place to place, and remember, we have two components here. Each component can, each index here is like a vector index. And here's the rule. Just make a blind eye to n. Just let's make a blind eye by circling it in red.
I'm confused about the P there. So would you want that to be the right-hand side on the board? Did you want that to be T?
Oh,
T sub P?
I wanted a p over here on this. Let's see. On one side, I want p. Thank you.
Yeah.
Yeah, p over here. Yeah, and also over here. Right. Okay, so we're doing a similar thing now to tmn. First of all, let's turn a blind eye completely to n. Whoops. Really blind. And we'll do that by circling it and ignoring it on both sides of the equation. If there was no n here, this would just be a vector. Let's write down what we would do to write the covariant derivative of t. The answer would be derivative of tm with respect to yp. I'm going to just never say n. Derivative of tm with respect to yp plus gamma m, gamma pmr times trn. Look what I've done. I've done exactly what I did over here, except with an extra index here, just riding along, just traveling along for the ride, doing nothing. But that's not the whole story. The rest of the story is to add another term in which you turn a blind eye to the index m. So now let's be blind to m. Ignore it. And write another term, which will be gamma pn. Now the index of interest is n, again r, and tmr. Let's see, this time which one did we, yeah, no, that was okay. That stays like that.
Turn the blind eye to m then.
Now we turn the blind eye to m. So m just went along for the ride over here in the second term. For each index, let's concentrate on covariant indices. For each index in a tensor, no matter how many of them there are, when you covariantly differentiate it, you get another term with a gamma times the tensor itself. And the other terms, the terms are simply one by one. You go through the various indices, turning a blind eye to all the other indices. That's the rule.
Clarify the middle term on the right-hand side of the equation.
This one?
Yeah. The subscripts of gamma are
PM and R, N went along for the ride. In other words, let's let's just erase n over here for a minute. First of all, let's get rid of this. I don't want to erase it because I don't want to have to write it again, but just forget it. And let's erase n. Then this would just be exactly the way a vector transformed. All right, but let's put back the blind index now, n. Okay. Now that's here. And let's turn our blind eye to the other index. Which one is the other one now? I lost track. Yeah, but yeah. In the second term, the blind eye is turned to the m index. So let's erase it on both sides. And notice, again, this is transforming exactly the same way that a vector would transform with an index n. You put them together, and you have the full transformation property, or not the full transformation, the full covariant derivative of a tensor. If there were more indices, you would simply have more terms exactly the same form, gammas times t's, but index by index, you would pretend it was a vector and transform it or do the same thing. That's the covariant derivative.
The t always occurs in the first term, and then
The derivative of t occurs in the first term.
right.
Yeah.
And it's always the first lower subscript in the gammas.
Yeah. Yeah. Yeah.
And then the rest in the
Yeah. That's right. So in particular, here's an interesting fact. You could have a tensor with completely constant components from point to point. Then there would be no derivatives, but still the covariant derivative of a tensor would be not zero. Somehow, this tensor has a covariant derivative, whatever that means. I'm going to show you an example in a moment, even though the components of the tensor are absolutely constant. Now let me give you an example of such a situation.
Is TNM
No, not in general.
So the m's went back into the wrong place.
Did I get them in the wrong place? You are right. I did get them in the wrong place. TMR, I think, right? Let's see. N is on the right side here, and M should be on the left side here, so that should be like that. Right.
In the first term, it should be MNT.
Here. Derivative, yes, you're right. Good. Thank you. Okay. But the basic rule is the same as the rule for vectors, except you go through it one by one, doing to each index what you did to the single vector index here. A scalar having no indices requires no extra term. All right. Now let's focus on this fact that there can be tensors, in particular vectors. Let's focus on vectors now. Vectors whose components are completely constant in curved coordinates, and yet the covariant derivative is not equal to zero.
I have a question.
Yeah.
I assume that you can swap an index with a repeated index. So
Yeah.
in the middle term there, you could have also written T sub n r if you wanted to.
No, you can't put an R here.
No.
Here.
T sub n r would have been okay.
NR. It is NR. You want R? No, not okay. Not okay. Not okay. You can't interchange in general.
No, that's a repeated index. So
N is not a repeated index.
no, r is.
Well, that means you can change it to S if you like, but you can't interchange it with N. You can give it a different name. That's fine.
Okay.
But you can't substitute one index for another. Okay. Unless it happens to be a symmetric tensor of some sort, in which case TAB is the same as TBA. Okay. Let me give you an example of a tensor or a vector which is clearly not constant, even though the derivatives of its components are 0. Go to polar coordinates. In polar coordinates, here's our polar coordinates. And let's consider a vector with the following property. Ignore the origin. The origin, as I said, is a nasty point, so we'll forget the origin, it's not important. But this vector has 0 for its theta component. What would a theta component mean? A theta component of a vector, the radial component of a vector, means the component along the radial axis. The theta component of a vector means a component along the tangential direction. All right, so now I have a vector where the theta component, let's call it v theta, is identically equal to 0. All right, but the radial component, let's say, is equal to 1. What does that vector look like? It has a radial, it has no theta component anywheres. Everywhere is on the plane. Its radial component is the same, equal to 1, but it points outward from the origin. That's a vector which has radial component equal to 1 and theta component equal to 0. Quite obviously, the components are constant. The components are constant, 1 and 0, but nobody would look at that and say that the vector field was constant. It's varying from place to place. Obviously, the vector over here is different than it is over here. So here's an example of a vector field whose components are constant in a particular set of coordinates. Their components would not be constant in Cartesian coordinates. In Cartesian coordinates, here it has an x component, here it doesn't have an x component. But in polar coordinates, the components are completely constant, and yet the vector is not constant. All right? What would happen if we calculated the covariant derivative of this vector? We would find that it's not 0. Right? We would find that it's not 0, and so it's the covariant derivative which picks up the real geometric fact that the vector varies from place to place. Now, I haven't told you what gamma is. Gamma is an object which can be constructed from the components of the metric tensor. So let's see if we can make a little bit of progress in finding out what gamma is. Okay. What about the covariant derivative of the metric tensor itself? Let's go to Cartesian coordinates first. In Cartesian coordinates, the metric tensor is what? What is the metric tensor in Cartesian coordinates? It's just delta mn. It really is constant from place to place. In Cartesian coordinates, it's absolutely constant. And incidentally, if an object is constant in Cartesian coordinates, where the coordinates don't flop around and change direction, if an object is constant in Cartesian coordinates from place to place, then it's really constant.
Well, I think you pointed out before that you could have a non-flat space with Cartesian coordinates.
No, Cartesian coordinates means coordinates in which the metric tensor is delta mn. It's not just that it's not just that they've laid out coordinates like this. It means that the metric tensor is equal to delta mn. That's what I mean. It means the space is flat, and it means that the
You mean the Euclidean or Cartesian?
I mean, when I speak about Cartesian coordinates, I'm now speaking about the flat blackboard. I'm speaking about a flat space with rectangular Cartesian coordinates. That's what I mean. So the metric tensor, if I took some other space, for example, I take the surface of a sphere and I lay it out on a plane by Mercator projection. Okay? Then you draw the Mercator projection, and it looks like it has Cartesian coordinates, but the metric tensor is not constant from place to place. That's why Greenland looks bigger than South America, because the metric is not uniform from place to place. Okay. What I mean by Cartesian coordinates, I mean Cartesian coordinates in flat space. The metric is just delta mn. Right? This is clearly constant, and if the space is identical at all places, the coordinates don't flop around, not only is the derivative of the metric tensor equal to 0, it makes good sense to say that, to expect that the real covariant derivative of the metric tensor is also 0. What would it be if not 0, if everything is exactly the same from point to point and the space is completely flat? So it's natural to expect that the covariant derivative of the metric tensor, let's write a dr of gmn of y is equal to 0. Now, why do I write that? I expect that the covariant derivative is going to be 0 in the x coordinates, but the covariant derivative is supposed to be a tensor. And if a tensor is 0 in one set of coordinates, it will be 0 in all coordinates. So it better be that if I've defined the covariant derivative correctly, then in flat space like this, it had better be that the covariant derivative of gmn is also equal to 0. That's a property of the metric tensor, that its covariant derivative is equal to 0, which is another way of saying physically it doesn't vary from place to place, and in particular in Cartesian coordinates in flat space it doesn't vary at all. Okay, let's assume that's true. Let's take that as given, that the covariant derivative of the metric is equal to 0, and let's see what it says. And we'll do it by, well, just by substitution here. GMN. GMN, GNS, and GMR, I think. And this should be equal to 0 if the covariant derivative of the metric is equal to 0. This is an identity which, if you struggle with it a little bit, you can actually solve it for gammas in terms of derivatives of G. I'm not going to work it out on the blackboard. It's a little bit tedious. You can either look it up in a book or you can try working it out yourself. A few tricks you need to write down. You need to write down a few. I'll tell you what to do when we get to it. I'll tell you what the solution of this equation is. Regard this as an equation for the gammas. It's an equation for gammas in terms of G's and in terms of derivatives of G's. That's what it is. Since G with lower indices multiplies gamma here, supposing I wanted to get rid of G with lower index, I have something which, let's first of all write that this thing here is equal to minus derivative of G, what was it? Oh, yeah, I lost the derivative with respect to YP of GMN. Yeah, approximately that. Okay, so here I have an equation. If it didn't have two terms like this, it would be very easy to solve. I would just multiply by the inverse of G. I have a gamma times a G, and G is an invertible matrix. So all I would have to do is run through the invertible matrix, and I would wind up with a G inverse. I would wind up with a gamma, something like PMS, with a derivative of G on this side, and a G inverse, lower components here, and a G with upper components here. Just by inverting G and bringing it over to the other side. It will bring an inverse of G to the other side. Is that clear? What we're doing then. But because there are two terms here, it's more complicated. It's more complicated. I'm going to write down the answer, and then what you do is you go home and you check that the answer that I write down satisfies this relationship. So I'm going to write down what gamma is, and it's your job to go home and check that if you plug in for gamma, it really does satisfy this condition. So I'm going to write down what it is. Anybody know what these things are called? The gammas? I forgot to tell you. They're called Christoffel symbols. They're called connections. Affine connection, Christoffel symbols, whatever you like. Christoffel symbols, not Christoffel.
They're not called gammas.
They're called gammas too. Yeah.
There's a lot of things called gammas.
What's that?
There's a lot of things called gammas.
Yeah, but not too many of them with three indices like that. So, right. So if you want to give them their right name is Christoffel symbol. There are all kinds of things which are called connections. They're all similar, and they're all related. They all are doing the same kind of job in various contexts. But in geometry, in this metric geometry like this, these objects are called Christoffel symbols.
Isn't there a Christoffel symbol of two kinds?
Yeah, but they're just related by raising and lowering indices. Yeah.
I just noticed it looks like you can lower indices on those two terms, can't you?
Which two terms?
The right-hand side there.
Yeah, you could, indeed. You could pull, this could be written as gamma PM with another index n downstairs. Right, and how about this one over here? This one could be written as gamma P N M. They're identical, except one of them has MN, the other one has NM. Okay. So they're not the same. In general, they're not the same. You can't obviously equate them. They're not the same. And for that reason, you can't just solve this equation by saying that this thing is basically half of this thing. Not so. It's more complicated. But I'll write down what the answer is, and you can check that. In fact, yeah, let's write down the answer. All right. I'm going to use other letters now so that we don't confuse them with the letters here. I'll use A, B, and C. Gamma A, B, C is equal to 1/2 G, A, D. I need another letter of the alphabet. That's going to be a summation index. And then it's the sum of three terms. Three terms. Each one has a derivative. Each term has a G with a super index here, upstairs index, and then derivatives of G with lower indices. It's just the indices are a little bit intricate. GAD times the partial of the derivative of G, let's see, what is it? DC with respect to XB. DC with respect to XB plus the partial of G. Now let's see, wherever I see B, C, G, D, B with respect to XC minus the derivative of G, B, C with respect to XD. Yeah.
Question is there, when we were over on this other board, we were doing a derivative with respect to the y coordinate.
Oh, sorry. Depending on whether, in any coordinate system, it has this form. Right. So if I was working in the y coordinates, I would put y there. Right. But then, of course, I would use the metric in y coordinates. Metric in y coordinates, if I wanted these, and this would be the Christoffel symbol in y coordinates. Now, the Christoffel symbol itself is not a tensor. It's not a tensor. For example, one way to see that it's not a tensor is if we were in conventional Cartesian coordinates in flat space, the derivatives with x coordinates, the derivatives of g are all 0. So this whole thing would be 0 in x coordinates. On the other hand, if we changed coordinates to some other kind of curvilinear coordinates, the g's would not be constant anymore, and the Christoffel symbol would not be 0. So the Christoffel symbol is not a tensor, but it's to be used in conjunction with tensors to construct covariant derivatives. That's its whole goal in life, is to be used together with the rules that I outlined for constructing derivatives of tensors. It's the extra term, or it's a piece of the extra term which is there because the coordinates wiggle from place to place. All right, so your job then is to take this expression, feed it into here, and check that what you get on the left-hand side is just dg by dy. That's the...
Is there a simple explanation where the half appears from?
I don't remember.
Or 2 pluses and a minus, and that's you got it.
Forgot, I don't remember. It's a, I don't know. I'm not sure why. If we plug it in, it ought to work. I don't remember. Oh, yeah. And important thing is, look at the structure of it. The BC components, in one term you have B downstairs, in the other term you have C downstairs. Those come in with plus sign, and then the last component has D downstairs. Okay, you can play with it and work it out. But the important thing about it, it's not so important exactly what it is. You can memorize it if you like, or don't memorize it. But the important thing is, it is the connection, it is the object, which allows you to differentiate tensors. Derivative of Vm with respect to xn plus gamma n mr vr. Covariant derivative. Okay.
Here's a funny, strange question. Is there some kind of convention, or like you have downstairs indices that are underneath the line, and then you have downstairs indices above the line, over here on the right-hand side, right? So you have y sub b is a downstairs index, okay?
It's a downstairs index. It's upstairs in y, but because it's below the line, it's downstairs, right?
You have 3 downstairs indices, but it isn't obvious to me what the order of those indices should be written as if you wrote them all as downstairs.
You mean this one too?
No, I'm just the part inside brackets. Basically, we have 3 downstairs indices, but should I call that VDC or DCB? If I was thinking of it as one entity with 3 downstairs indices.
It's not symmetric with respect to them. It is symmetric with respect to B and C. It's symmetric with respect to B and C, but not with respect to D. And that you can see because there's a minus sign here, among other things.
It has 3 downstairs indices.
Yeah,
Okay.
it does.
Until we contract it with the G.
Yeah. So we could call it
But
gamma B, C, D.
okay, so you would put BCD. Okay.
No, it's got two downstairs indices plus a third one.
Okay.
Uh, You just have to remember which one goes where.
You just have to, okay.
And it happens, if you look at it carefully, you'll see that it's interchange symmetric with respect to B and C, but not with respect to D.
I thought the D disappeared.
Yeah, but nevertheless, we have to give this thing a name in here that gets multiplied by GAD. And then the D disappears. But before we disappear it, we give it a name. Okay.
Using G to raise and lower indices, that works with non-tensors as well?
It happens in this case, it does, yeah. It happens in this case. And furthermore, you can use gamma to differentiate contravariant tensors also. For example, I'll show you the rule. The same object, as it happens, enters into the derivative of contravariant tensors, contravariant components of tensors. For example, if you have a vector with an index n, now it has an upper index n, again, y components, and you want to differentiate it with respect to ym, that itself is not a tensor. For the same reasons, the contravariant components also depend on the direction of the axes. So as the axes move around, you've got to keep track of that. And the derivative of the contravariant components are not themselves tensors. Right? This would be a tensor with one upper index and one lower index, but it's not. You have to add something to it. And the thing you have to add to it has gamma. Now it has a lower index m, an upper index n. We're going to have to put in another index. Let's call it r. That's going to be a summation index. And then a vr of y. So the same set of objects is useful in differentiating things with upper indices. Once you construct this family of objects, and there's a lot of them. How many of them are there in three-dimensional space? 3 times 3 times 3, 27 of them. In four-dimensional space, it's 64. Of course, they're not all independent. They do have some symmetries. But there's a lot of components, and so if you're actually doing some computation, you might want to write them all down in your notebook, make a list of them, what they are, what their values are, and then start playing with them. So it's a tedious business working out these things, but the logic, it's the logic that I want you to understand, that differentiating tensors and doing it in a way that gives you back tensors is a slightly complicated process that involves a new thing, namely the so-called connection or Christoffel symbol. That's the basic lesson. Okay, yeah.
So the reason that the metric has a zero covariant derivative is because it's zero in Cartesian, and it also must be zero in the other.
Yeah. It makes a lot of sense to say that in the Cartesian coordinates in flat space is the same everywhere. It makes a lot of sense to say the basic object in that space is constant from position to position. You don't have to define it that way. You could have defined some crazy definition, but in flat, homogeneous space, the blackboard going on and on forever, perfectly flat and perfectly homogeneous. Homogeneous means the same everywhere. It makes good sense to say that the metric has no variation from place to place. So in the flat coordinates, the tensor that you would make by differentiating the metric would be 0. Once it's 0 in one coordinate system, if it's a tensor, then it has to be 0 in all coordinate systems. And so one comes to the conclusion that the covariant derivative of the metric should be 0. That's what we use to find a basic relationship which, when solved, gives us this formula. Yeah.
Do you have a way of looking at at the derivative, the covariant derivative of a vector that doesn't involve the coordinates. In other words, you're taking the nearby things and doing something to them, and what precisely is it? I mean, here we've gotten a lot of information.
Well, okay. Yeah. It's very hard to describe what you're doing without introducing coordinates. But maybe it helps a little bit, the following idea. Any space, any Riemannian space like this, spaces with metrics like this are called Riemannian spaces. Any Riemannian space, curved or not curved, locally, that means if you look at a very small patch of it, looks like flat space, is indistinguishable from flat space for a small enough region. That means on a small region there, you can introduce Cartesian coordinates. You can introduce perpendicular coordinates, and you can even do it so that the derivative of, first of all, so that the metric at that point is delta mn, by introducing, on the surface of the Earth is not flat, but just drawing two perpendicular great circles, basically. Wouldn't even realize they were great circles if we're looking in some small region. We just think they're straight lines. And introduce locally, in the vicinity of a point, Cartesian coordinates. Then the metric at that point, the metric will just be delta mn. But it's possible to do even a little better than just saying that the metric is delta mn at a point. It's also possible to keep the coordinates straight enough and perpendicular enough so that the derivatives of the metric at that point, at a single point, are 0. So that up to first derivatives, the metric is constant and just of the form delta mn at a particular point of space. With a given set of, with a given space, you can't make the metric constant everywhere unless the space happens to be flat. If the space is flat, you can make the metric like this everywhere. But if it's not flat, you can go to a particular point and do that. Now, there was a reason why I raised that, but I forgot what the question was, though.
We're talking about the derivative, the covariant derivative.
Yeah. Covariant derivative of what?
Say vector.
A vector.
You can see from the formula that what the
Yeah.
covariant derivative is simple has to be 0.
Yeah. Okay. So what it means, at such a point, if you go to these locally Cartesian coordinates, then the locally Cartesian coordinates like this, the derivatives of g at that point are all equal to 0. And at that point, focusing on that particular point, the covariant derivative is just the ordinary derivative in those coordinates. In other words, you erect as close as you can get the flat space, the flat coordinates to Cartesian coordinates. You can't do that everywhere simultaneously, but you can do it in a tiny little region, and then the covariant derivative is just the ordinary derivative in those kind of coordinates. So it's telling you how the vector varies in coordinates which are as flattened out as is possible to make.
How the vector is turning and growing at the same time.
Yep, turning and growing.
In each direction.
Right. That's right. Yeah.
So if gamma is 0, is that a definition for flat space?
No, that's not quite right. If you take flat space and you use curvilinear coordinates, then gamma is not equal to 0. Remember, gamma is not a tensor. It depends both on the nature of the space and the coordinates that you use. In flat space, what is true is that it's possible to find coordinates in which gamma is equal to 0. But it's also possible to make coordinates in which it's not equal to 0. Here's an exercise. Work out the gammas for polar coordinates. There are gammas for polar coordinates. Why is that? It's because at least one of the components of the metric, GRR, is equal to r squared. that means the derivative of GRR with respect to R is not equal to 0. That begins to give you the possibility of having a Christoffel symbol in polar coordinates. And there is a Christoffel symbol in polar coordinates. That just means in polar coordinates, when you differentiate a vector, you'll have to include, remember what happened with the vector which had constant components in polar coordinates. It wasn't really constant. So in polar coordinates in flat space, covariant derivatives are not entirely trivial. And that means that there are Christoffel symbols for polar coordinates. What is true for flat space is that you can find coordinates, namely just your good old rectangular Cartesian coordinates in which the metric is just delta mn, in which all the Christoffel symbols are 0. In a general curved space, you cannot do that. In a general curved space, in general, the Christoffel symbols will not be 0. Yeah?
Is the term external derivative the same as covariant?
Say it again?
External derivative? I see that.
External, you mean exterior derivative?
Exterior, yes.
Completely different thing. It is a kind of derivative for sure, but the exterior derivative is a tensor. You know what the exterior derivative of a vector is? In 3 dimensions? It's the curl of the vector. It's called an exterior derivative. So we won't get into that now. Yeah, the exterior derivative is a tensor, but if we ever need it, we'll come to it. Let's I don't want to stop tonight. I want to continue tonight because I want to get finished with this, with the mathematics, so that we can start thinking about physics. All right, let's take, let's see, what do we need to do here? Yeah. Supposing I have some curve. Now, let's start with ordinary flat space, ordinary conventional flat space. I have some vector field which varies from place to place. In particular, I can evaluate that field along the curve. And I want to know how the vector field varies just along the curve. Ordinary flat space. What do? I want to know how the components of the vector vary along the curve. This is easy. We just write the field. V, let's say the nth component of it, again, as a function of y. And I want to know how it varies. First of all, I want to invent a parameter that varies along the curve. What's a good parameter that varies along a curve? Arc length, length along the curve. We can start here and call it 0, and then measure in some units, whatever units we like, distance along the curve. And of course, we call that s. In the same sense that we call ds squared the square of a little interval, we can invent a variable along the curve, which is just arc length along the curve. I would like along the curve to ask how v is varying. How do I do that? Well, I differentiate it. Well, let's take first a scalar. Take a scalar. How does a scalar vary along the curve? Its derivative along the curve. In particular, its derivative with respect to the parameter s. We evaluate it on the curve, and I want to differentiate it with respect to s. So I'd like to find along the curve the derivative of phi with respect to s. Whoops. Just telling me how phi varies. Well, if I know how phi varies throughout the geometry, I just write d phi by ds, the dx m, let's say. That's the partial derivative. And then what do I do to make it into the derivative along the curve? We multiply it by dxm by ds. So everywhere along the curve, there's an object dxm by ds. That, of course, is a vector. dxm is a little vector, and when I divide it by ds, s is a scalar, just the distance along the curve. dxm by ds is a vector. You know what that vector is called? The slope would be dy by dx. I mean, dx1 by dx2. So it's connected with the slope, but it's not quite the slope. It's a vector. First of all, it's not a number. It's a vector. It has two components, dx1 by ds and dx2 by ds. Okay, let's look at it a little more closely. Here we are along the curve. We take a little interval of size ds, and we look at dx. Here's dx. It's the vector dx along here. First of all, what direction is it in? Tangent to the vector, tangent to the curve. And how long is it? What's the length of dx by ds? Yeah, 1. Why is that? Well, it's 1. It's a unit vector along the curve. It's called the tangent vector. It is the tangent vector along the curve, a unit vector along the curve called the tangent vector. Okay? All right, so that's what, here's what you do. If you want to differentiate phi along along s, you differentiate it with respect to the coordinates. That gives you a covariant vector, and you multiply it by the contravariant vector dx by ds. And that gives you the derivative of phi with respect to s. Right? Very simple. Now supposing we want to differentiate a vector, or a vector, not a tensor, not a scalar, but a tensor, in particular a vector, along a curve. Well, you might think the right thing to do is basically the same thing. Take the vector v. Let's take a contravariant vector. It depends on x, I guess. Well, x and y are the same thing here. X. All right. And now what do I do with it? Well, differentiate it with respect to position. X, what did we call it? X, let's call it n. M times dxm by ds. This actually gives us the derivative of the component of v with respect to s. But would you guess that this is a tensor? It's not likely to be a tensor because the whole thing is not likely to be a tensor because the vn by dxm is not a tensor. Remember, the ordinary derivative of components of tensors is not itself a tensor. So this object is not a tensor. It doesn't represent, let's see why. Well, it's the usual reason. Even if v were completely constant along the curve, and what would that mean? That would mean it's completely constant, pointing in the same direction everywhere along the curve, because the coordinates flop, not because the curve is floppy, incidentally, but because the coordinates are floppy. dv by dx won't be 0, and so even for a vector which was absolutely constant in space like this wouldn't be 0. So,
Those are Cartesian coordinates.
no, I'm not assuming they're Cartesian coordinates. Right. No, particularly not. No, I guess I should have stuck with my convention, x being Cartesian, so then we should use y here. All right, so let's use y. Well, what can I do to make a vector out of this, a tensor out of it? A tensor that varies along the curve. Well, we just replace this by the covariant derivative. Wherever you see ordinary derivative, replace it by covariant derivative. At least the covariant derivative has the property that if the vector isn't really varying, the covariant derivative is 0. All right, so if we replace this by the covariant derivative, that's just covariant derivative with respect to m of v n of y times the tangent vector. That we can think of as the covariant derivative. The notation for it is it's the covariant derivative with respect to the parameter s of v n. In other words, we've defined a covariant derivative of a vector along a curve. How? You just take the ordinary covariant derivative and you multiply it by the tangent vector. Tangent vector just tells you what direction you're differentiating in. You take the covariant derivative, and that defines the covariant, the path derivative along the curve. Important concept. Okay. In particular, it has the property that in Cartesian space, in flat space with Cartesian coordinates, if the components are constant, then the vector doesn't vary along the curve. Okay, that's the notion of the covariant derivative of a vector along a curve. Just good. Let's write it out in detail. Let's write it out in detail. What is it? It's the derivative of Vn with respect to ym times, well, let's add the other term. What's the other term? All right, tell me where to put the gamma, the indices of the gammas. Where does the n index go? It's upstairs. It better go upstairs in the gamma. The m index has to go downstairs, and then we need another index and write Vr. That's the covariant derivative of V. Then we have to multiply it by the tangent vector. So let's multiply it here by the tangent vector plus dy m by ds, dym by ds. What is this thing over here? The derivative of the component, the nth component with respect to y, times dy by ds. Chain rule, right? This object over here is just the derivative, the ordinary derivative with respect to s of Vn. So along the curve, we differentiate. It's the first term, but then there's another term, and the other term is gamma nmr. The vector that we're differentiating times the tangent vector. So if I have a vector which is defined along a curve, and I want to differentiate it along the curve in a way that makes it a tensor, I just differentiate its components, and then I hit it with a gamma along the curve. The gamma is defined along the curve, times Vr, and also multiply by the tangent vector. You see the pattern? Okay, now let's go another step. Let's ask how the tangent vector varies along the curve. For v, let's just put in the tangent vector itself. And then I would be asking how the tangent vector varies along a curve. Here's the tangent vector. And obviously, in general, the tangent vector varies from place to place. In particular, if the curve is a curve, on the flat blackboard, the curve is really a curve, then the tangent vector varies. We can work out the covariant derivative of the tangent vector. Let's do it. What's the component of the tangent vector? For Vn, we're going to substitute dyn by ds. That's the component of the tangent vector. And I'm now computing the covariant derivative of the tangent vector itself. The covariant derivative along the curve. So let's just plug it in. First of all, what do I get for dvn by ds? That becomes the second derivative of yn with respect to s. It's just the derivative with respect to s of the derivative of y with respect to s. So that's a second derivative. A certain second derivative of y along the path length. And then what's the other term? Gamma mrn. Let's write down, what is it, dym by ds. And then v is just dy r by ds. So the first term is just the second derivative of y with respect to s. And the second term, look at it, it has an m and an r downstairs. It has a dy by ds, a tangent vector, the mth component, and a tangent vector, the rth component. Nice and symmetric with respect to these two. And it has an extra index representing the uncontracted index here. This is the covariant derivative of the tangent vector. And the covariant derivative of the tangent vector is a tensor. That means if it's 0 in any reference frame, it's 0 in every reference frame. What do you expect the covariant derivative of the tangent vector of a straight line to be? 0. If I have a straight line in flat space, the tangent vector is the same everywhere. So if I am in flat space and I have some funny coordinates, which aren't ordinary flat, ordinary Cartesian coordinates, but I give you the tangent vector, I give you the components of the tangent vector and the Christoffel symbols and so forth, that's what you know. How do you test if it's a straight line? Its components are not constant because the coordinates aren't constant, they flop around. How do I test whether my vector, whether my tangent vector, whether the curve is a straight line? Well, I compute the covariant derivative of the tangent vector, and if it's 0 all along the line, all along the curve, then that curve is a straight line. It's just telling me that the tangent vector is unchanging as I go along the line. You could do this with funny coordinates, even if those coordinates aren't flat coordinates. Now, can it be that in curved space, really curved space, a general space which cannot be brought to the flat form because there's some obstruction called curvature, which it doesn't look like we'll get to tonight, but can it be that the covariant derivative of a tangent vector can be 0 anyway, even though the space is not flat? What would you guess? Yes. What are curves whose tangent vectors are covariantly constant? Covariantly constant is another way of saying the covariant derivative of the tangent vector is 0. Here it is. Where is it? Here it is. Supposing I have a curve. A curve means some y. A curve means a curve. Y's, and along the curve has a set of coordinates y that depend on how far along the curve you are. Everywhere along the curve, y is given. Here's the tangent vector. Can it be that the covariant derivative of the tangent vector is 0? It certainly won't be true for every curve. In flat space, it's only true for straight lines. Can it be true in a general curve space that you can find curves, special curves, which have the property that the covariant derivative along them is 0, covariant derivative of the tangent vector? The answer is yes. And those curves have a name. Geodesics. Geodesics are, if you like, the straightest possible curves in the space. They have the property that the covariant derivative of the tangent vector is 0. In particular, that means if you take coordinates locally, which are as flat as possible, then the components of the vector are constant for a little ways until the coordinates start to bend. But a geodesic, that's the general definition of a geodesic. A geodesic is a curve whose tangent vector is covariantly constant. Covariantly constant means that the covariant derivative of the tangent vector is equal to 0. And that's it. That's the definition of a geodesic. So, in a certain sense, it's the straightest possible curve in the space, or it's a family of curves. Yeah.
A quick question. You define this all in terms of a covariant derivative.
Yes.
Could you just as arbitrarily used a contravariant derivative and get to the same point?
Yes, you could have used. Yeah, we could have used. Sure, definitely. We could have used the contravariant covariant. Wait, sorry, just a moment. The term covariant derivative does not mean that the object is a covariant vector. Completely different use of the word. It's unfortunate. This is the covariant derivative of a contravariant component. Too bad, that's the way it is.
But like the key point is the inclusion of this gamma thing.
Yeah, that's right. That's right. Now, just to tell you where this is going, let me tell you where this is going. Straight lines in space-time, in special relativity space-time is flat. Straight lines in space-time are the orbits of particles that have no forces on them. Okay? The orbits of particles that have gravitational forces on them are geodesics in space-time. That means they satisfy equations like this. Now, if you look at this equation and you think of path length along a world line as being like time, ticking off time along the world line, then this is almost like acceleration. It is. It basically is acceleration. We don't want to prove this now. We just want to tell you where it's going. This looks like the second derivative of a coordinate with respect to a parameter. And that parameter could be proper time. It would be proper time. So it's essentially a relativistic version of acceleration. What does this say? It says that acceleration is equal to something on the right-hand side. What would you call that thing on the right-hand side? Force. Right. So where we're going eventually is that this is the equation which determines the orbits of particles in a gravitational field. The force is proportional, first of all, to the Christoffel symbol. That's the most important thing about it. Forget these things for a moment. They're there, they're important, but here's the important thing. What does this contain? It contains derivatives of the metric with respect to position. How about Newton's equations? What's Newton's equations for the motion of a particle in a gravitational field? It's F equals ma, right? All right. F equals F. Ma is mass times the second derivative of position, let's call position y, with respect to time. It looks sort of like this. And then what's on the right-hand side? The gravitational force. But what is the gravitational force proportional to? Well, in general, in a general gravitational field, it's proportional to the mass times the derivative of the potential, the gravitational potential. Let's call it, let's give it a name, phi or v, I don't know, v, u, v, with respect to y. Masses cancel out. You can see there's some similarity, an acceleration type term being related to derivatives of something with respect to position. What are the Christoffel symbols? They're composed out of derivatives of the metric with respect to position. So somehow we're going to find that the derivatives of the metric with respect to position are the analogs of the Newtonian gravitational force. That's where we're going. So I thought I would tell you rather than just blindly write formulas on the blackboard. Particles move on geodesics, which means the straightest possible paths in space-time. But of course, you can't have a completely straight path in a curved space. And deviation from what you might think of as straight is proportional to these gammas. So the gammas are very, very closely related to gravitational force. They are the gravitational force. What else can we say at this point? Yeah, we haven't gotten around to curvature yet, but we have all the apparatus that we need. We need one more concept, namely the concept of parallel transport, but I will tell you what that is next time. Parallel transport, and then we will get to the idea of curvature. We have some ideas that are going to be useful for how particles move. Next, we need to understand more deeply the obstruction to spaces being flat, to flattening them out, and that's curvature. Okay, we're done.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.